Okay, so finally, as I promised, now we are going to see the power series method to solve some ODEs with non-constant coefficients. Okay, so um, let's start. We can think about this power series method in several steps. So the first step would be, okay, I have my ODE and I will assume that I have a solution that admits a power series representation. So what's the idea of the method? Look at this solution. If you remember, the characteristic equation method was about suggesting a particular solution of the form exponential to the power lambda x, and then we were looking for which values of lambda are give us solutions of the equation, right? So this has the similar idea. I propose certain type of solution, I suggest this solution, this power series solution, and now all will be focused in try to find these coefficients am. So it's the same idea as we did with the characteristic equation method, in the sense that we propose a solution and with some parameters, in that case was lambda, and then we look for those values of lambda that really give solutions for the equation. So here is exactly the same. We propose this type of solution, a power series solution, and now all the energy will be focused in try to find these parameters, these coefficients am. Okay, so the first step would be, okay, I assume I have this type of solution. Second step, we write the ODE as a power series, as we were working in the last example in the second part of this lecture, second lecture. So we take our ODE and we write it as a single power series. Once we have that, we equate coefficients of the resultant series on both sides of the ODE. So hopefully now with the example we identified each of these steps. So I hope it's clear when we see the example. Step 4. Find the unknown coefficients am in the series representation of U. So as I said, first we propose this solution. Now all the energy is put here and try to find this am. So to this aim, we write the equation as a power series. Then we equate the coefficients that we have in both sides of the equation. And this step 3 would lead us to the unknown coefficients am. Maybe. So we'll see. Okay, let's try to identify and solve this equation, identify these steps, solving this example. We have a second order because here we have a second derivative. And we have an initial value problem, we have these initial conditions. And okay, here there is a 1 next to the second derivative of u, there is a 1 next to u, but there is an x here. So we cannot apply in this equation the method of the characteristic equation, because this is not a constant coefficient equation. The coefficients of the equation are not constant because of that x. But that's why we saw this power series method. So let's try to apply this new method. We assume the solution take this form, power series representation. We write the equation as a power series. So this is the equation. So we have 0 is equal to this expression. So let's work with the expression. Here is u. Here is u prime. Remember that we get a -1 and m here and the same coefficient. And let me see, here is the second derivative of u. So remember that we differentiate term by term. So if we differentiate with this term, we get this one. And then if we differentiate this one, we get this one, where we have m minus 2 and this m times m minus 1 here. Okay, and here there is this x. Remember, we can shift indices now, but I strongly suggest that first we make some calculation, and once we are done with that, we shift indices at the very end. Okay, so another remark before doing that, remember that the second derivative starts at m equal 2. The first derivative starts at m equal 1. So pay attention with that. Okay, so we distribute this x and we get xm. So that's nice, because now this one and this one will be already written in as we want, with x to the power m. So as we said, here we have a nice power. So those are already finished, let's say. And we have to work a little bit with this one. Why? Because we have m minus 2 here, and we really want to write this expression as a single power series. So we really want to have x to the power m there. So we can add at the end the term by term. Okay, as we were doing before, we call this n or k or the letter you want. Let's put n. And then we have an expression of m. So in each time m appears here, we have to work with n plus 2 instead of m. And now we pay attention of which values this n can take. So m starts, this power series starts at m equal to 2. So we have 2, 3, 4, and so on. That means that our new parameter n, which is m minus 2, takes the values 0, 1, 2, and so on. Okay? So we rewrite this term here. M equal to 2 now goes to n equal to 0, and m minus 2 goes to n. And now pay attention, because now we have to write all these terms in terms of n. So, as we said, m is equal to n plus 2. Here we are. N minus 1, if we look at here, is n plus 1 here. And please don't forget to change also this this m with the m inside the coefficient am. That also has to be changed. So what we get is n plus 2. And now, since the other terms are with the index called m, we just go back to m, which is just change the name. It's exactly, everything is the same, but we go back to the letter m. Okay, so now we are almost done with step 2, because now we have, going back to this expression, remember that we are rewriting the equation as a single power series. So we go back and we have this power m, power m, power m. So that's great. And then we pay attention to where each power series starts. So here m0, which is nice because they are the same. And here is m equal to 1, but exactly as the last example in the second part of the lecture, look at this m is multiplying the coefficient am, and we when multiply by 0 is exactly 0. So we can change this m equal 1 to m equal 0, and we will have exactly the same power series. So that's what we do here, which is exactly what we did in the last example in the second part of the lecture. So now we have the expression, everything with m equals 0, started in m equals 0, sorry, here, and we just add this term by term. So here we have the first term that you can see here, second term that you can see here, and third term that you can see here. Okay, and now these two guys can be also written again here. So finally we have this expression as the coefficient of this new power series. And this is the step 2, right? We took our equation and we rewrite it as a single power series. Okay, so step 3 was equate the coefficient. So now here this number 0 can also be seen as a power series. The power series constantly 0, where every coefficient is equal to 0. So equate coefficient here in this example would mean that for every m, this amount has to be 0. So that's what we have here. 0, oops. Okay, we have to wait a second. So we have 0 is equal to this expression for every m. No, I don't want to do that. Okay, so sorry for that. Going here to the coefficients. So we have 0 is equal to this expression, and then we can work a little bit with this expression to get that this coefficient am plus 2, we can compute this coefficient in terms of am. And simplifying a little bit, what we get is this final expression, am plus 2 is equal to this number times am. So this expression has a name, which is the recurrence relation, and as we can see, we can compute the coefficient m plus 2 if we know, let's say, the previous one, not exactly the previous one, because the previous one would be m plus 1, if we know 2 steps before, which is the coefficient am. Okay, and that it's called the recurrence relation. Okay, so final step is, once we have this recurrence relation, we wonder if we can really compute and say, okay, a0 is equal to 1, a1 is equal to 5, a2 is equal to 3, and etc, etc. So we really want to find these coefficients, to determine these coefficients, so we can have the complete expression of our solution, which is a power series. So it's all about to find this coefficient. We will use this recurrence relation to see if we can find them. How we use this recurrent relation? We just choose this one by one the values of m, because we have this relation, sorry, it's not written here, but we have this relation for every m equals 0, 1, 2, and so on. So first step, we choose m equals 0. So we do this calculation for m equals 0. If we put 0 here, 0 here, 0 here, what we get is a2 is equal to minus a0 over 2. Okay. So if we choose m equal 1, what we get here with m equal 1 is a3. M equal 1, here we have a 3 and a 1. And we do this for these values of m. M equal 2, you can see that you get a 4 here, minus a2 there, but now we can use that we already know that a2 is this. So we put this information here, and we finally get that a4 is 1 over 8 a0. So if we choose m equals 3, we will know a5, which is this expression. But again, we already know who a3 is, so we put that information here, and then we get this. And we can do this with many values of m until we convince ourselves that we know who are these am, these coefficients. So if you pay attention, you can see that for 2, 4, 6, we have a0 involved. Well, here is not the final result, but we have a0 involved. And then for 3, 5, 7, and so on, we have a1 involved. So in some sense, what we have here is that for 2, 4, 6, and so on, a0 determines those values of am, and for the rest, 3, 5, 7, and so on, a1 determines those values. So what I'm trying to say is that a0 determines the coefficients with even indices and a1 with odd indices. And if you work a little bit, you can see how these terms are related, and you can prove that we have for even indices this expression with a0, and for odd indices this expression, the whole expression with a1. Okay. So, step 5, which is not in the described in the method, as we remember here that we have 4 steps, but we can add this new step. It's related with these initial conditions. So once we solve the equation and we know the coefficients am, notice that we have a0 and a1, that we don't know them, but we have these two initial conditions. So with these two initial conditions, we will finally determine a0 and a1, and that would give us the whole expression of the solution u. So we go to this step 5 here, and we use the initial conditions to determine a0 and a1. So the first initial condition was u at 0 is 0. Remember that u is this power series, so when we evaluate this in 0, at 0 we get exactly a 0, so we have a0 is equal to 0. And the derivative of u at 0 is equal to 1. This is the expression of the derivative of u, and now we evaluate it at 0. So we get a1. That means that a1 is equal to 1. So now, this expression of the coefficient now can be finally determined because we already know this. This is 0, so all of them are 0. And this is 1. So finally what we get is this. And eventually we have the final solution. The solution of our second order initial value problem is given by this expression. So those coefficients are equal to 0. So the m equals 0, 2, 4, 6, 8 don't appear. And then we have those x to the power 1 minus 1 over 3 x to the power 3 plus 1 over 3 times 5 x to the power 5, and so on, which follows this rule here. And we have this expression, and this is the solution of our problem. Okay, so in this lecture, in the whole lecture 2, we first saw power series, and we studied some properties of the power series, how to operate with them, the radius of convergence, the interval of convergence, how to find those things, which we have these two methods, these two tests, the root test and the ratio test. And then once we learned how to work with power series, in this third part of the lecture, we saw the power series method, and we have this description of the power series method with these steps. So if you follow the steps, you will be able to solve the exercises. The exercises that we have in this section. And here you have an example. It's all about proposing a solution which has the power series representation, and then try to find these coefficients am. How we do that? Okay, we rewrite the ODE as a single power series, which the properties that we learn in the second part of the lecture. And once we have that, we equate the coefficients and we find this recurrence relation. And sometimes we will be able to really calculate, not with this recurrence relation, just with the numbers, like A0 is equal to this number, A1 is equal to this number, and so on, and not giving with the recurrence just independent values. So how usually we get those independent values? Just computing, using the recurrence relation to compute the first terms, and giving that usually gives an idea of how is the general formula for AM, not in the recurrence way, just explicit formula for AM. Once we have an explicit formula of AM, it might happen that the explicit formula depends on the first values, A0 and A1, or A0, A1, and A2, or some finite amount of the first steps, the first terms. And then, if we have initial condition, we will be able to determine those values and finally get the real expression, the final expression of the solution, which we proposed, and is a power series. Okay, as usual, if you have any questions, you can contact me. And just one more comment that I almost forgot. When can we use this power series method? So because we said that, okay, we can use this power series method when we have ODEs with non-constant coefficients. So here is a rule or a fact of when we can use this power series method. So imagine that we have three functions, p, q, and g, and the three of them admits a power series representation at this point A. Then the ODE, this one is a second order ODE, has a power series solution centered at the same point A. So here is where we can use this method. If we have, for instance, this ODE, and the coefficients are functions, but they admit a power series solution, a power series representation, and then we know that we can assume that we have a solution which is a power series in the same center as these three functions. You can check that our example verifies that. And just last one more comment. If we are in this situation, that point A receives a name, has a name, is an ordinary point for the equation. Okay. So that's it for today and for the power series method. Here there are some exercises, but also this information will be on Blackboard, so you don't have to copy that now. And as usual, if you have any question, you can contact me.